My name is Varyn Ebner, and we're going to talk about cephalopods. Specifically coleoid or shellless cephalopods. Octopuses, squids, cuttlefish. And yes, it is octopuses or octopods. Octopi is a lie sold to us by Big Cactus. So we can all agree cephalopods are awesome, right? Thank you. Like, really, if you don't think cephalopods are awesome, can you raise your hand right now? Seriously? Just kidding, you stay, and by the end, you will agree with me. So cephalopods are the only branch in the animal kingdom outside of vertebrates that developed a large brain, not to mention the mini brain in every single one of their arms, and camera-type eyes. They're the most sciencey of animals. They developed these eyes separately, though. It's a case of convergent evolution, where two traits or systems developed entirely separately and then converge on a similar form. And they're, in fact, almost exactly alike. Within the coleoids, though, there is a great diversity of form and function, and in most cases, I'm going to be talking in broad strokes. And also, a lot of this is based on theoretical models that we don't fully know a lot about, so you can take everything with a little bit of a grain of sodium chloride. So if you're soft and squishy, your best defense mechanism is to camouflage. And even better if you can hide in plain sight. So cephalopods have a lot of reasons to camouflage, and they're very, very good at it. They use it to hide from predators, they can ambush prey, and they can also use it for intraspecies communication, so mating displays, and they even warn each other about predators. They can nearly instantaneously match both the pattern and texture of their background. This is known as rapid adaptive camouflage. They can also mimic other animals. And some of them can even maintain this camouflage as they're moving. They even have what's known as dynamic nocturnal camouflage, and this has never been seen before in the animal kingdom. So how do they do this? Well, there's a couple different facets to this, but we're going to start by going skin deep. Like other ectotherms, or cold-blooded animals, think reptiles, amphibians, fishes, they have these specialized cells in the skin called chromatophores. They're color change cells. Chromatophores, they also have subclasses. They contain different pigments, such as the melanophores have brown to black pigments, the erythrophore have red pigments, and so on. How they work: they're elastic color change cells, and they're surrounded by radial muscles. When the muscles are relaxed, the cell is essentially a pinpoint. It's pretty much invisible. But when the muscles contract, they spread the cell flat and allow the color to appear on the skin. Science the fuck out of this, yeah. So here is, it's kind of a more detailed diagram of the cell, because cells are complex, and then also some really cool microscopic slides showing the chromatophores, and you can see the radial muscles branching off. Chromatophores, however, are just one layer. There are two other classes of color change cells, the iridophore and the luciphore. Sounds kind of metal. The luciphore, meaning white, luciphore reflects ambient light through crystals, and it doesn't change the wavelength of the light. So essentially the light is white. However, if the ambient light is at different wavelengths, it reflects those wavelengths. So it reflects the color of the surroundings. But iridophores, they're inherently colorless, and they're reflectively iridescent. So they're reflecting and refracting lights. And in fact, a lot of squid species have the same control over iridophores as the others have over chromatophores. The iridophore has two main uses. One is that it creates light and color that is visible only at certain angles or dependent upon direction and movement. So for one, they can use it to coordinate schools. It's also able to redirect light for what's known as counter shading. This is where a surface of an animal matches the background lights. And since they can control this, cephalopods can do this from any angle. Here's a cuttlefish displaying iridescence, pretty cool. They can also redirect polarized lights, which cephalopods are uniquely equipped to see, giving them essentially a secret channel of communication. Some cephalopods, especially deep-sea species, have photophores. So these are chemically induced bioluminescent cells. And while some are simple, others are complex with lenses, filters, and reflectors that allow them to change the nature of light. They can redirect it and even tune the wavelength to change the color. And they can also change the texture of their skin. Under the skin are these protuberances known as papillae, and they're controlled by superficial muscles that allow them to express as anything between small bumps and large spikes. And of course, here we see the papillae on an octopus giving us the finger. And allows them to produce things like this. So we're gonna go now deeper into the skin and into the brain. We know other ectotherms can change color, but they do it more slowly, right? That's because it's hormonally controlled. However, with our cephalopods, the changes can be nearly instantaneous. And this is because the color change cells are wired directly to the brain. Here's an example, the fin nerve of the cuttlefish, and it goes directly to innervate the fin chromatophores. In fact, the majority of the cephalopod brain is devoted to visual processing. 2/3 of the brain is made up of optic lobes. Nerves extending from these lobes are directly connected to those radial muscles that change the cell's shape. So much science. So how does the brain translate this visual information into complex patterns, and how does it do it instantaneously? We know it can't be a learned skill. We know they're not pondering their surroundings. The answer, well, we don't know for sure yet, but there are theories. Cephalopod eyes do a lot of the same thing that our eyes do, but their vision is very different in some key ways. The only neurons in the retina are photoreceptors. These detect and respond to light. They detect spatial scale, intensity of contrast, and depth information about their surroundings. Also, note here the strangely shaped pupil and how they're off axis. That will come in a moment. But there's a plot twist because cephalopods are colorblind. Science? Okay, so they're not strictly colorblind, but they definitely don't see color in the way that we do. So there's only one photopigment in their photoreceptors, and it sees color on the blue-green color scale. So how are they detecting color? One theory has to do with their ability to see polarized light. So they might be collecting the information around them by sensing and interpreting the refraction of light. This would also give them an advantage, as they would see an increased contrast, they would be able to detect transparent objects, and they would be able to see better in murky conditions. They also have photoreceptors in their skin, so that might be partially responsible. And another theory is that they might use something called chromatic aberration or chromatic blurring. This is where different wavelengths, they don't focus all at the same point, but instead come into focus at different distances from the lens. This is something that photographers try to avoid, but cephalopods might actually take advantage of. So they're strangely shaped pupils. They increase chromatic blurring, and they would be moving across a scene, and they would be changing the distance between the lens and the retina, essentially changing the focus, and then detecting and monitoring how the blurriness changes, and then this could be translated into information about what the color is. Side note, they color change even when they're asleep. What? Does this mean that they're actually dreaming? Actually, we can't know that unless they could tell us, but it does mean they have sleep cycles like we do. So let's see. adjustment, stand by. To wrap up, there is a scientist named Roger Hamlin. He fell in love with these creatures early on in his career and devoted his life to studying them. He's sort of a celebrity in the marine biologist world, and I wrote him a letter, and he wrote me back the next day. Scientists are so cool like that. So I asked him for his most memorable experience studying cephalopods, and he came back with this. My single most amazing experience was following an octopus with a camera. He had the camera, not the octopus. And as I approached very closely, it suddenly blanched bright white with a dark ring around the eye, then inked in my face and jetted away. This is known as the wow scene and has been in many TV documentaries. Show this to your nerdy friends. Yeah, I told them y'all were nerds. Okay, let's see. Where's it gonna go? Stand by. Yes, there we go. Here's to the awesome cephalopods, you nerds.